Today, we are going to look at a more realistic refrigeration cycle. And in the previous lecture, we talked about the Carnot. Of course, there was the extra problem that we talked about, and we solved a couple example problems related to the Carnot cycle. But the Carnot refrigerator has some interesting limitations that you'll find in that video about what you can and can't calculate, etc. But what I want to do in lecture today is to start to think a little bit more realistically about how refrigeration cycles are set up and how they're operated. And to do that, I'm going to start by drawing an analogy with the Rankine cycle. And if you remember, our Rankine cycle had 4 unit ops in it, right? So one was a pump, then there was the boiler where we added heat, and then we went through a turbine. And then finally, we had a condenser, right? And essentially what we were doing was we were pumping liquid water, saturated liquid water to high pressure. And then we were converting that into steam. And then it would get expanded through the turbine, then fed to a condenser where it becomes saturated liquid again. And then you would go through the pump. And the working fluid, which was often water, in the Rankine cycle was just continuously transferred between steam and water and steam and water and steam and water. Okay. Now, if we're going to look at a vapor compression cycle, which is the typical refrigeration cycle that we're going to be looking at, there are still 2 stages where we are going to heat the gas, or where we're going to heat the fluid, and we are going to cool the fluid. And we're actually, where we add heat, which again in a refrigeration cycle is at the cold temperature, is in the evaporator. And then we're going to remove heat in a condenser, but again, the condenser is at the higher temperature. And remember, the difference between a power cycle and a refrigeration cycle is that in a power cycle, you add heat to extract work. In a refrigeration cycle, we're going to do work to remove heat. And so in the power cycle, we had a turbine where we were getting work out. In the vapor compression cycle, we now have to do work, and that's going to be in the compressor. So we're going to have a stage where we have a compressor. And then in the power cycle, we increase the pressure using a pump. Well, in this case, we're going to try to do the opposite. So instead of having a pump, we're going to have a valve. Okay. And our cycle is going to go in this direction. Okay, and we'll talk through the steps here in just a second. Okay, but that is refrigeration, or the vapor compression cycle. Okay, and in that cycle, there are 4 steps, just like there are in basically all of the other cycles we've looked at. And so in our vapor compression cycle, step 1, we are going to have saturated vapor that is compressed reversibly and adiabatically.
Wait, Dr. Mustaine, are these the steps for the refrigeration?
Yes, they are. And you know what? Just to avoid that confusion, let's do this. So we've already made our analogy. So I'm going to get rid of that and move that over. Okay. And so this is our steps for the refrigeration cycle. So step 1 is to compress saturated vapor reversibly and adiabatically. And if you think about where we are, let me actually label this as A, B, C, and D. So step 1 is here, right, in the compressor. Okay. And then step 2 is going to be to remove heat at constant pressure, right? Because we're going to undergo a phase change until you have a saturated liquid.
You said constant pressure?
Yes. And then step 3 in the process is going to be reduce the pressure through a valve. And remember, when we were looking at valves earlier in the semester, we assumed that these were throttling valves. And what that really meant after we manipulated the energy balance was that they are isenthalpic, okay? That the change in enthalpy through a throttling valve is equal to 0. And then step 4 is that the fluid is heated back to saturated vapor at constant pressure. Okay. And I already drew step 1. So step 2 is if we're going to remove heat at constant pressure until you have a saturated liquid, you're condensing the liquid, right? So that's step 2. Then step 3 happens here in the valve. And then step 4 here is our evaporator. Okay. So in this cycle, we have a really interesting difference, though, than something that we had in our power cycle. So in the power cycle, we had 2 steps that are reversible and adiabatic, right? So we had 2 steps where delta S was equal to 0. And because of that, using the temperature entropy diagram, right, TS diagrams made a lot of sense. But in the vapor compression cycle, we actually are also operating between 2 pressures, right? And they're 2 saturated states. And this is something that's kind of important for us to think about, is that A is saturated vapor and C is saturated liquid. And so when we're operating on this particular cycle, where we are on these sort of property energy diagrams is going to be very specific, right? Because if you remember in the TS diagram, right, that we had this phase change. So we know that we're going to be on this phase change line twice. But that begs the question of, is the TS diagram the most useful diagram that we could possibly have? And so if we think about this, right, we already said that we have saturated vapor and saturated liquid, but we also have a throttling valve, right? We have this step where we know that delta H is equal to 0. And because of this, that we're able to operate under 2 saturated conditions where the pressures are constant, and the fact that we have a step where delta H is equal to 0. For refrigeration cycles, it's much less common to use a TS diagram, and it is much more common to use a pressure enthalpy diagram. Okay, and I know that you guys haven't seen one before, so I'm going to start by showing you an example for a pressure enthalpy diagram. And so that's right here. And you'll notice that the shape looks really similar to the TS diagram. So here, instead of temperature being on the y-axis, it's pressure. Instead of entropy being on the x-axis, it's enthalpy. And what's happening is that we have these isotherms that come down. They meet the saturation line, and then you have phase change as you go from the left of the green curve all the way straight across to the right, just like we would have in the TS diagram. And then at constant pressure, or sorry, at constant temperature, as you reduce the pressure, you increase the enthalpy. And so you're still moving down and to the right here. And so this is a pretty simple example of a pH diagram. And if we think about where we might be in a diagram like this, well, let's draw one. So if we drew a pressure enthalpy diagram, and let's have the same phase change region that we had in the TS diagram that you just saw previously. Let's think about where we are. Well, again, at state A, we are at the lowest temperature and pressure, and we're a saturated vapor. And so we would be approximately here, right? So that would be state A. And then at state C, we're saturated liquid at the highest temperature and pressure. Okay, so we're there on the curve. And because step 3 is at constant enthalpy, we're going to have a vertical line where we drop the pressure through the valve, right? And so we're actually here. So that's state D. So right, we're moving in this direction on the pH diagram. Now, for state B, we're going to go through a compressor. If the efficiency is 100%, that will be done isentropically. But our endpoint is at the same pressure as C. So that's a straight line across to B, then here to C, which is saturated liquid, and back down where you have a mixture. You know, if you go through this valve isenthalpically and you start with saturated liquid, some of it is going to vaporize. And so that's one of the things also to note at state D, that it is a mixture of liquid and gas. And so if we just draw the steps, just so everybody's clear, right? That's step 1. That's step 2. That's step 3. And that's step 4 in our pH diagram. Okay? So before we talk about anything else or do anything else, does anybody have any questions just about the overall process here?
I don't think so.
All right, so if not, one of the key steps here when we're evaluating the cycle is that step 1 is done reversibly and adiabatically, right? Or the change in the entropy is equal to 0. So one of the things that we need in evaluating these refrigeration cycles is to introduce entropy onto the pH diagram. And so to do that, I'm going to show you a more typical pressure enthalpy diagram, and it is considerably more complex. And I'm going to try to step through this relatively slowly. So hopefully you guys can see that we have our saturated line here, right, where we have saturated liquid and saturated vapor, okay? Now, also on this plot are the isotherms that I showed in the more simple diagram that's here. And I'll draw those in a different color so that where I'll draw one in a different color. And so you can see that the temperatures are listed here. And hopefully you see that. This one says T equals 20 degrees C. So let's just follow that line. Well, those are essentially vertical lines. And so T equals 20 degrees C is this line, and it goes here. And then we're going to go straight across here, and then we'll pick it up again right here. Okay, and that is one of the isotherms, okay, at constant temperature. And there's a whole bunch of them. And you'll see that above the critical temperature, like here at 200 degrees, that one never touches the phase change regime, right? And that makes sense, right? If you're above the critical temperature. Then the other thing that we're going to find important on this diagram are the lines of constant entropy. And the lines of constant entropy are these, right? So this says the entropy is equal to 11.0 kilojoules per kilogram Kelvin. So here is one line of constant entropy. And there's another one. Okay. And so on this curve, there's a lot of information. There's even the fraction of vapor, right? Or the quality of the fluid. There's also lines of constant density, but those last two we don't actually utilize all that often, at least not when evaluating the performance of such a refrigeration cycle. So as long as on a diagram like this, you can identify where the saturation lines are and where the lines of constant temperature are and the constant entropy lines, we should be able to actually assess a refrigeration cycle. And in fact, a refrigeration cycle is one of the problem types where it is most often solved on a diagram, not necessarily through tables, because we have the steam tables for steam, but we're not going to operate refrigeration cycles on water almost ever. And thinking about why that might be would be a good thing in the context of the problems we're going to do today, because that's one of the homework questions is why wouldn't you do that? And so there's not an extensive array of tables. Refrigerants also often cannot be assumed to be ideal fluids, right? Or certainly not ideal gases, because there's some of the time we're going to be in the liquid phase. So just like we talked about in the Rankine cycle, to evaluate this process, we're going to try to determine the enthalpy at each one of these locations. And fortunately, we have a diagram that we are going to be able to use to do that directly, right? The pH diagram has the enthalpy right on its x-axis, okay? So if that's the case, I'm certain you're not yet comfortable with pH diagrams because you haven't actually seen one used. But if you guys kind of get what we're doing in the cycle, let's solve a couple of example problems. And hopefully that can help you guys to become a little bit more comfortable with the pH diagram. And then of course you'll have some practice with it on the homework. And so the first problem that we are going to solve today asks us to design a cycle that uses ammonia to cool a freezer at minus 15 degrees C and expel heat to the atmosphere. To do this, we assume that the freezer coils operate at minus 20 C, right, to encourage heat transfer from the actual freezer to the coils, and the condenser is at 80. So our two operating points in our refrigeration cycle are minus 20 degrees C and minus 80 degrees C. And so one of the things then that we're going to try to do is to figure out on our pH diagram that we drew previously where we are located, right? And we know that state A is here, and it's the saturated vapor at our lower temperature, right? So that's at minus 20 degrees C. And then here we're going to be at state C, which is at 80 degrees C. And because they're saturated, we'll know what the pressures are because we'll be at minus 20 degrees C and whatever P sat is at minus 20. And here we'll be at P sat at minus 80. And then we will find all the rest of these points, right? So that's A, B, C, and D, okay? Okay, so let's do this. All right. So I've actually pulled up the pH diagram for ammonia, which is the focus of this particular problem. And when I start looking at solving a problem using a pH diagram, I've already said a couple of times that we know the two states of, or we know two of the states, right? We know that A exists at -20, and we know that C exists at 80, and they are saturated. So let's find those on this diagram. And I know that it looks like a big mess of numbers. So for -20, we could either start here and go down and across, or we know that -20 is going to be here, and it's right there. And so all we need to do is actually follow the line from -20 up to the point that it intersects the saturated vapor line. Okay. And now that we've done that, we should be able to read off the pressure and the enthalpy. And so I'm going to do my best here. I'm not particularly great at drawing horizontal lines without a ruler, and I'm certainly not going to put a ruler on the iPad. So that's about as good as I can do. So the pressure here is around 0.18 megapascals. And if I go straight down from here, as good as I can, the enthalpy here at state A is approximately 475 kilojoules per kilogram. And one of the things that you'll notice about this diagram is that it's not very well broken up into segments, right? So, I mean, you could just as easily draw a straight line down and say, I think that's more like 470. And so, one of the lessons here in a refrigeration cycles, even if you did this and your numbers are a little different, when we start to calculate things like the coefficient of performance, it'll be really similar. And it's something that we're just going to have to be, reasonably comfortable with. The other value that we have to measure, or at least record here, is the entropy, because we know to go from A to B, we're going to have to follow a line of constant entropy. And so we know the entropy at A is also equal to 10.6 kilojoules per kilogram Kelvin. Okay. All right. So we know some stuff about state A. So let's keep moving forward here. And the next thing that we know for sure is the state at C, right? So we know that we're saturated liquid at 80 C. And so we can find that up here. And here's the line for 80 C. So I'll follow that straight down and place the dot right there on that line. And we can do the exact same thing that we did just a second ago and figure out where we are. Well, if I draw a straight horizontal line, sorry, let me retry that just a little bit. There we go. That line's better. So at 80 degrees C, we know that the pressure is 4 megapascals. And again, we can go down, straight down, and measure that the enthalpy at C is approximately 375 or minus 375 kilojoules per kilogram. Okay. So we have the first two states that are saturated. And every time you solve a problem like this, I really do suggest that you do exactly this, that you find A, the saturated vapor condition going into the compressor, and then you find C. Because once you do that, the rest of, or finding the other 2 points are relatively simple. So the first one is that we know that the valve, which will give us state D, is isenthalpic. So we actually could just draw a straight line, and that intersection with the lower pressure, right, that's state D. And then the last point that we're looking for is B. And here we're not told anything about the turbine, or sorry, the compressor efficiency. So it's going to be 100%. And so we're just going to follow this line of constant entropy up until we reach the higher pressure. And so if we do that, we can move along here, and we're going to be right about there, right? And that's state B. And if I go straight down from there, my estimate for the enthalpy at B is equal to 975 kilojoules per kilogram. And so what we have on our diagram is the enthalpy at all 4 places, okay? Now, before we do any more calculations, does anybody have any question about how I use the diagram?
To find B, you follow the constant entropy?
Correct.
Okay.
Yeah, and you'll notice the constant entropy lines, they're sort of curved, right? So you'll have to make an estimate. So, you know, here, that was about 10.6 at the bottom down there. And so all I did up here was try to get to a point where it was about a fifth of the way between the 10.5 and 11.0 line, okay? And that's because, remember, A to B, this is the compressor step. So in this part of the diagram, we are here, right? We're in the compressor when we go from A to B. And we were told that unless you're given an efficiency, it's done reversibly and adiabatically. Okay? Good question. All right. So are we okay?
Yeah, someone wants to know how you got point A in the chat.
So point A, remember in the problem statement, that's a good question, is that we're told that the freezer coils operate at 20 degrees C and the condenser is at 80 degrees C. And so at this lower temperature, right, this is saturated vapor at the lower temperature. And so if that's true, then all we need to do in our diagram is to find the saturated vapor. And the line, right, the saturation line, so this side's liquid, and here's the saturated line for the vapor. So all I did was I found the line for -20, which is admittedly pretty, or at least somewhat difficult to read. And I just followed it up until it intersected with the saturation line. Good question. This is also something that I will post on Blackboard. So we're going to use 2 pressure enthalpy diagrams today. I'll put those on Blackboard so you guys, you know, can print them if you want to and actually do the exercise. Okay, because I think it's easier oftentimes to actually that it's easier to actually do these, right, as opposed to just watching me use the diagram. All right, so hopefully that'll help you guys. All right, so now we've read the enthalpy off of each point in the process, and we have then our cycle, right? So we know where we are on this diagram. So the last thing that we really want to do here is to determine the coefficient of performance, okay? And for us, you know, we already defined the coefficient of performance as being equal to the heat absorbed at a lower temperature, right? So that's going to be Q for our step D to A, which is in the evaporator, okay? So that's Q evaporator divided by the net amount of work that's performed, okay? And in our process, the net amount of work, well, there's only work done in one step, right? We only compress because the valve is just a valve. So we don't actually do any work. We don't extract any work out of the process. So this is actually the work of our compressor. And so if we look at this, then Q for the evaporator is just the enthalpy at A minus the enthalpy at D. And the work for the compressor is the enthalpy at B minus the enthalpy at A. And if we do that, well, HA we read was 475 kilojoules per kilogram minus the enthalpy at D, which was equal to the enthalpy at C. And we went straight down, and that was minus 375 kilojoules per kilogram, then divided by the enthalpy at B, which was 975 kilojoules per kilogram, minus the enthalpy at A, which is again 475 kilojoules per kilogram, or for this process, the coefficient of performance is equal to 1.7, right? So it's greater than 1, just like it is for most processes, okay? The next thing that we could do here is compare this to the Carnot cycle. So we could look at what the coefficient of performance would have been in the ideal case. And remember, that was T cold over T hot minus T cold. And so our cold temperature here is minus 20 degrees C, which is 253.15 Kelvin. Our hot temperature was 80, which is 353.15 Kelvin minus the cold temperature. And that is equal to 2.5. So just like in a Carnot engine, or in a real engine, that it can never have an efficiency greater than the Carnot efficiency, in a vapor compression cycle or in a heat engine, it's or in a refrigeration cycle, that its coefficient of performance can never be greater than the Carnot coefficient of performance. And this proves that that's true for this particular cycle. Okay. All right.
Dr. Mustaine,
Yeah.
what was it in the problem statement that made you know to go about a fifth of the way from the entropy at 10.5?
Well, it wasn't in the problem statement. The reason that I knew to do that was because as soon as I found this point A here, is that I can read multiple things, right? As soon as I knew that I was a saturated liquid at minus 20, I could come up on this blue line and I could find where it intersects. And from there, I read off the enthalpy. And then remember, these lines of constant entropy are here. Here, I'm going to use a different color just so I don't confuse. But this is 10.5 here, and this is 11 here. And so I estimated that this was a fifth of the way, right? So the entropy here, I estimated as 10.6. So then in step B, or to get to B in the compressor, it's isentropic. So I know if the entropy here is 10.6, then the entropy here has to be 10.6 as well, right? And that's also sitting between these same two lines of constant entropy. Okay, does that make sense?
Yeah, that makes sense. Thank you.
All right, good. All right, great. So before we go on to the next example that we're going to solve today, does anybody have any other questions?
I have one regarding the graph. So on the other diagrams that we look at for sat vapor and sat liquid, can we assume that that line is somewhere in the middle on this one as well? Or do we even need to know that?
Are you talking about, I don't know if I understood your question correctly, but are you talking about here?
No, up at the top of the saturation curve. So like on the other ones, we always kind of split it in half and said, you know, liquids on this side.
Oh, no, that's also true.
Okay.
So that's still the critical temperature and pressure at the very peak here.
Okay.
And everything to the right here is saturated vapor, and everything to the left there is saturated liquid. Yeah, good question. Sorry, I misunderstood. Yeah, good question. All right, anybody else? All right. So if not, let's solve another example. So the approach here is going to be similar, but this time we'll use a different pressure enthalpy diagram. So this says that we have a vapor compression refrigeration system operating with tetrafluoroethane as the refrigerant, that it evaporates at -6, or the evaporator operates at -6 degrees C, and the condenser operates at 26 degrees C. Then we're told that the heat load is 2,000 kilojoules per second, and if the compressor efficiency is 75%, what's the power requirement? So we have a little bit of a different mission here in this problem. So we're not going to calculate the coefficient of performance. Instead, we're going to figure out first, how much power it takes, and we're also going to do something a little bit different than the previous problem, where the compressor efficiency isn't going to be assumed to be 100%. We'll assume that it's 75% and kind of talk through how we're going to do that. But the underlying thing that we want to do in this problem is actually the same as it was in the previous problem. That now I have the pH diagram for tetrafluoroethane, and we're going to do the exact same thing we did a minute ago. We're going to find A, we're going to find C, and then D, and then we're going to sort of solve the isentropic case for the compressor. And then from there, we'll be able to calculate the real work that's done in the compressor. Okay, just like we would have done if we had steam tables or some other fluid that we used in the past. All right, so I'm gonna paste that here and make it large enough that everybody can see it. And then let's go about solving this problem. Okay, so just like in the previous problem, right, we were told the two operating temperatures, right? We were told that the evaporator operates at -6 degrees C, and we're told that the condenser operates at 26 degrees C. And so what I'm going to do then is I'm going to find A and C based on those conditions. So again, I know, and actually Tamara brought up a really good point, that here's the saturation line, right? And that's all vapor. And on the line, that's all saturated liquid, right? And so, and I'm sorry if that's actually not so easy to read. So what I'm going to do here is I'm going to find -6 degrees C on the saturated line. And there are a few ways to do this. I don't see a good place here to find the temperature, but I do find a good place here. And we know because these are phase changes, right? We're going from liquid to vapor, that they're just horizontal lines on the pH diagram because phase change happens at constant pressure. So this line here is 0, and this here is -10. So if I'm looking at this and I know that I'm operating at point A is at -6, well, I'm going to find a point that's just a little bit beyond the middle of those two. Okay. And when I do that, I will immediately go straight down and try to read off the enthalpy, right? So that's state A. And for state A, the enthalpy, when I do that, is approximately equal to 395 kilojoules per kilogram. Okay. So I did that immediately. And the nice thing about this is it also gives us the lower pressure if we want to look at that. And so that's going to be right about here, right? Okay. And that lower pressure is about 0.23 megapascals, right? Or 2.3 bar. The second point that I'm going to find is C. So we know we're operating at -26 degrees, or sorry, at 26 degrees. So here we're at 20 and its line coming straight down. And here we're at 30 and its line coming straight down. So somewhere between those 2 points is 26. And I'll do the same thing. I'll just find the middle and go just a little bit positive of the middle, right? So to get to 26, and then I'll do the same thing I just did a second ago, and I'll draw the line horizontally on the diagram. And so now I have state A and C immediately in the problem. And then if I want state D, I just go straight down from C, right? So that's D, because that's still a valve. Okay. All right, so now let's find B. Well, to find B, first we have to solve the isentropic case, just like we would have done if we had for steam tables or any of the other problems that we solved earlier on in the semester. And so what I've done then is at A, I'm going to read off the entropy. And to do that, let's look and see where the lines of constant entropy are. So here's the first line of constant entropy here, right? And actually I drew that a little too straight. So yeah, here's one of them, and here's the other one. And so we're mostly right between the minus 1.7 and we're right between the 1.7 and 1.75 kilojoules per kilogram Kelvin line. So I'm going to say that the entropy at A, is something like approximately equal to, 1.73 kilojoules per kilogram Kelvin. And so I'm going to take my line at approximately that same entropy value up to the higher pressure. So here's 1.7, here's 1.75. And so we're right here, more or less. Right? So we're going to call that B for the isentropic case, right? So we've solved B when delta S is equal to 0. And I can read the enthalpy for B there, right? So maybe the better thing, instead of calling it B, we'll call it B prime, right? So HB prime is the isentropic case. And we can find that if we go straight down, I estimated it to be something like 417 kilojoules per kilogram, okay? Now, you might see 415, you could see 419, it would be pretty similar. But, when I did this and I had a ruler and I went straight down, each of these lines here are tens. And so I was able to get something that was like, we'll call it 417, okay? So now we have the isentropic case for B. Well, if we remember for a compressor that, delta H real for the compressor is equal to delta H for the isentropic case divided by the efficiency. And so we know then that delta H when delta S is equal to 0 is this HB prime that we found minus A, and we know the efficiency is 0.75. So that's just 417 kilojoules per kilogram minus 395 kilojoules per kilogram divided by 0.75. And so then our enthalpy, right, delta H real is like 29.3 kilojoules per kilogram. Okay. And so that value is actually more like here. Okay. So that's really where B is right there in the diagram. Okay, so does that make sense?
B is the Carnot and B prime is the.
Yeah, B prime was the isentropic case,
Gotcha.
and B is the real case that we have.
So what does it mean for something to be like further away from the saturation curve?
So as you move towards the right, it becomes superheated steam or superheated fluid, right? We're not using water here. So the farther away you get from here, right, everything to the right of here is just what we would call a superheated fluid. And if you look at what would really happen here, that as we move to the right, the temperature goes up. So just like we would have expected. So on this line, you know, this temperature here is about 30 degrees C here at B prime. And if you follow the lines, you know, of constant temperature, the actual temperature would be at about 43 degrees. So we would be at a higher temperature. All right, does that make sense? All right.
Yeah.
So we were also asked in this problem to calculate the power that is required to run this cycle for this heat load that's 2000 kilojoules per second. So when we're after the power, right, we're really after the work of the compressor, which is m dot delta H for the compressor. So we don't know what m dot is, and that's where the heat load comes into play. So we know, if we just put a pin on that for a second, that in our evaporator, that Q for the evaporator is equal to m dot delta H. So m dot just equals Q for the evaporator over delta H. And we're told what Q evaporator is, right? That's 2000 kilojoules per second. And then delta H for the evaporator is just HA minus HD. And so we know that HA was approximately 395 kilojoules per kilogram minus D. And of course, the enthalpy at D, because the valve's isenthalpic, is just the enthalpy at C. And reading that off the graph really quickly, that is about 236 kilojoules per kilogram. And so that gives us a mass flow rate of 12.6 kilograms per second. And so now we can do this, right? We can calculate the work of the compressor. So that's 12.6 kilograms per second times delta H for the compressor, which was 29.3 kilojoules per kilogram. So the work of our compressor is 368 kilowatts. The last example that we're going to solve today is an interesting switch on the problem that we just solved a minute ago. And in this problem, we still have the exact same refrigerant operating at the same temperature. So -6 degrees C in the evaporator and 26 degrees C in the condenser. But here what we've done is to institute a heat exchanger between the vapor stream from the evaporator and the liquid from the condenser. So if we have a look at how that might affect our cycle. So here we have our valve, evaporator, compressor, and condenser. And if we introduce a heat exchanger here, the new streams actually go from the outlet of the condenser through one side of the heat exchanger, and then the other stream leaves the evaporator and goes to the compressor. And the rest of the cycle is the same. We still go from the outlet of the compressor to the condenser, and then from the valve into the evaporator. And because the design points are the same, right, that we still want saturated vapor leaving the evaporator, and we still want saturated liquid leaving the condenser, that's still point A, and it's exactly the same as it was in our previous problem, or our previous go through this problem, and then there's point C. But the thing that's going to change here is that when we go through the heat exchanger, we're going to go to some higher temperature at the same pressure. And that state we're going to call A prime. And then leaving C, we have C prime, and then we have B and D. Now, because we enter the compressor at a different temperature, B will not be the same as it was in the previous problem, and D will not be the same where it was in the previous problem, because through the valve is done at constant enthalpy, and now we'll be at C prime. We won't be at C. Now, from the problem statement, we do have one more piece of information, and that is that the minimum temperature difference for heat transfer is 5 degrees C. And the reason that's important is because if you think about how we might operate this heat exchanger, well, we know that the temperature in the condenser is 26 degrees. And if the minimum difference in the temperature is equal to 5 degrees, that means that the difference in the temperatures between state C and state A prime is equal to 5 degrees C. And if C is still at 26, and that is our design point, that means the temperature at A prime is 21 degrees C. And so now we know at least what that condition is going to be. We also know in this process that delta H for our condenser is equal to minus delta H, or maybe minus delta H of C to C prime in the heat exchanger is equal to minus delta H from A to A prime. And so mathematically, right, that gives us that we know that the enthalpy at C prime minus the enthalpy at C equals minus the enthalpy at A prime minus the enthalpy at A. Or the enthalpy at C prime is just HC plus HA minus HA prime. And so once we know the enthalpy at A and the enthalpy at A prime, we can actually pretty easily find the enthalpy at C prime and then D. And that's what we'll do. So first we'll find A and C, just like in the previous example with this cycle. Then we'll find A prime, then we'll find C prime and D, and then we'll find B. Okay. Now we're going to leverage the same method that we just did a moment ago, where again we're going to solve this using a pH diagram. And so the pH diagram from our fluid again is right here. And if you recall, the temperature of the evaporator is -6, and that's saturated liquid, so that's here. And then, or saturated vapor, I'm sorry. And then at 26 degrees, we have saturated liquid, and that's state C, right? So that's A. And then 26 degrees is here, and that is state C. And we'll do the same thing that we did previously, where we'll draw straight horizontal lines so we know what the operating pressures are for this process. Okay. All right, there we go. All right, so we have A and C. So now let's find A prime. Well, A prime is, or the step from A to A prime is also done at constant pressure, right? We're not going to do anything in the heat exchanger to significantly reduce or increase the pressure. So now we're basically just going to move to the right from A until we reach 21 degrees, which is right here. Okay. And so what we can do then is, now that we have A, C, and A prime, we can find the enthalpies at those conditions. So we know the enthalpy at A is 395 kilojoules per kilogram. We know the enthalpy at A prime is equal to 420 kilojoules per kilogram. And we know then also from reading the graph that the enthalpy at C is about 236 kilojoules per kilogram. And so using the equation that we've written above here, we can find the enthalpy for HC prime. So the HC prime equals HC, which was 236, plus HA, which is 395, minus HA prime, which is 420. And that's 211 kilojoules per kilogram. And so again, what we're going to do is at constant pressure, because it's before we go through the valve, move. Now, instead of to the right, we're going to move to the left until we reach an enthalpy of about 211 kilojoules per kilogram. And so that's about here. Okay, so this is actually C prime. And what this means is that going into the condenser, we now have superheated fluid, right? And it's just at a higher temperature. And then here we also have a subcooled liquid. And now what we'll do is to find state D is you go straight down, right? Because we're still going through a valve. So that's still isenthalpic. And so now we have this transition from D to A prime. And we know to go to C prime, from C to C prime, and C prime to D. So the only thing that we really have left to do in this problem is to find where we are with respect to B. So we know that the efficiency of the turbine is 75%. And the first thing we'll do, though, to get there is to solve the isentropic case. And in the isentropic case, right, we start here between these two lines of constant entropy, just like we did before. And now we're going to move up, right? And so this is sort of what we would call B when delta S is equal to 0. And if we want to, we can find the enthalpy of B when delta S is equal to 0. And that number here, if you read it off the plot, is about 445 kilojoules per kilogram, okay? And so we can calculate delta H for the compressor. And we know that delta H for our compressor is equal to the isentropic case divided by the efficiency. And that's just equal to HB when delta S equals 0 minus HA prime divided by the efficiency. And so that's 445 kilojoules per kilogram minus 420 kilojoules per kilogram divided by the efficiency. And so that is equal to 33.3 kilojoules per kilogram. And so if we wanted to, we could find the exact location of B, right, the actual B, and that would be at 420 plus 33, so about 453. And so that would be right about there. And so if you move up, right, that's B. And now we have our total cycle here, right? That we're going to B to C prime, to D, to A, and to A prime. Now we can find the same two parameters that we found when we solved the previous case. So if you recall that we use the fact that the mass flow rate is just Q evaporator over delta H for the evaporator. And Q for the evaporator was 2,000 kilojoules per second. And delta H for the evaporator is just 395 minus 211, right? It's the state. This is the enthalpy at A minus the enthalpy at D. And that is equal to 10.87 kilograms per second. And then finally, we can calculate the work for the compressor, which is just the mass flow rate times delta H for the compressor. And that's equal to m dot times H. Well, we actually calculated that, right? That's HB minus HA. So if we plug those in, that's just 10.87 kilograms per second times 33.3 kilojoules per kilogram. And that gives us a work for the compressor equal to 362 kilowatts. And interestingly, in this problem, for the base case, the compressor work was 368 kilowatts. So there wasn't really a huge change in the work that needed to be done. But what did change was the mass flow rate. And so here it's 10.87. In the previous version of the problem, right, without the heat exchanger, it was over 12. And so that can affect things like how would you size the equipment, which could have capital cost implications, even if it didn't really have electrical cost implications.